Okay, welcome everybody for the first public code of the month session. So we will present in a monthly series the flagship codes of the Centers of Excellence for High Performance Computing. And today we have the great pleasure to host Gabriel Staffelbach from CERFAX, which is part of the CUE EXCELLERAT, and he will present the code AVBP. So please, Gabriel, the floor is yours.
Thank you very much. Hello, everyone. So thank you for coming for this presentation. So just a quick word about CERFAX. CERFAX is a research center focused on training and technology transfer using HPC. The idea of the lab that is located in Toulouse, as you can see on the map, is to concentrate competences on HPC, numerical methods, and modeling to tackle scientific problems. And with three scientific teams, one on global change, basically what the name suggests, so change of the way of weather patterns, long-term, short-term, algo co-op, which is more algorithmics and computational science, and CFD, computational fluid dynamics. This work is in part done in collaboration with partners from industry and academia. The industrial partners that work with CERFAX are the ones that you can see here for Total Energy, CNES, Onera, EDF, Safran, Airbus, and Météo France. As you can see, big actors on the energy, propulsion, aerospace industry. The code AVP is the property of CERFAX. It's a compressible Navier-Stokes finite element solver that works on unstructured multi-element grids. You can see a sample of the grid on the right, for example. You can use arbitrary Lagrangian Orion methods for moving grids or automatic measure adaptation. I'll come back to that a bit later. The principle behind the code is large edge simulation, where you focus on the large scales and model the small ones. Numerical schemes are up to the third order in time and space. And since the main application of the code is combustion, we use reduced and analytically reduced chemistry models. The code can do two-phase and the gaseous phase simulations with Eulerian and Lagrangian approaches, so particle tracking. The thermodynamics can be perfect or real gas for complex thermodynamics applications. And since most of the applications require the study of the acoustics of the setups, we have accurate characteristic boundary conditions. Regarding the AVP community and the AVP code, the code is not open source, but it's what we call an open science code. So the code can, access to the code for research and non-compete activities can be requested directly at CERFAX. We have here a sample of people using the code or have access to the code. So TU Munich, TU Berlin, ETHZ, University of Sherbrooke in Canada, VKI in the past, CNRS, a couple of labs in France. This is the list, the non-exhaustive list. There's also industrial own usage for some partners, and also industrial usage by bilateral agreements. So people contact us to do some work on their industrial applications. Here are some examples of the people using the code for in-house activities and so on. The code has about 30 contributors annually, mostly PhDs. These are at CERFAX, so I'm not counting external contributors. And there's about 30 to 40 papers annually on the code. Here, of course, I'm counting also external papers, not only CERFAX. The code itself, it's 500,000 lines of code and uses the SPMD parallel approach with domain decomposition. It's mostly written today in Fortran and C, and it can use MPI 1 and 3 for parallelization. It has full GPU offload for reactive gaseous phase, and only with static grids, and for NVIDIA GPUs, and on AMD systems that come from with the Cray compiler. The multiphysics approach is possible with the code, so basically code coupling. For that, we use a coupler called Sweepy from Onera, and we're able to add to the fluid dynamics thermal, radiative, and structure coupling. And we have also coupling with AI that I will explain at the end. Now, our strategy regarding the code for in HPC is in this pyramid, as you can see on the left. Basically, we have the lower end, which are you could say closed systems or partner systems, where people do confidential work or contracts, basically. And then you go to the tier one system that are the national systems in France, where we give support to the community, so the people from France use these systems, and we also use them for academic purposes. And on top of that, you have what used to be praised, now it is your HPC, and also specific access when a machine is new, where we do what we call early adopters or hero simulations, or very big industrial applications that require 50 or 100 million CPU hours minimum. And of course, there's also fringe technologies and tests like what we do with API, trying for example, the RISC architecture from BSC or Graviton from Amazon. And you can see some of the partners for these porting activities and HPC activities on the right, the usual suspects in the world, that you could say. Now, regarding applications, the code focuses mainly in combustion. So one of the applications we have done is for aerospace propulsion. So this is a real experimental test bed from DLR with 42 injectors that we did on the IREN Gen C system at TGCC. And it's, as you can see, basically rocket and simulation that was done on 132,000 ROM Milan cores on the code. Regarding the performance, on the left here, you have the scalability of the code for two test cases. In green, you have the rocket engine you just saw up to 132,000 cores. And in triangles, you have a turbulent channel, so an academic channel, done up to 65,000 cores, just to show you that it's not just one case scenario, it's, the code works for multiple cases. And the slope is different because the initial point is different. One starts at 64 nodes and the other at 32, but basically we have almost perfect scaling up to these big CPU systems. One of the things that we have worked on EXCELLERAT was, of course, this parallelization and this scalability, but also single node performance on demonstrators. Here on the right, you can see the comparison between Intel architectures and the Amazon ARM architecture Graviton. This is for full node. So you can see the computation efficiency. So lower is better. And the Graviton in this case is better because it has much more cores, but we're able to use them efficiently. One of the main results of the phase one of EXCELLERAT was working on the port to GPU using OpenRCC for NVIDIA. These are the results that you see on the left. On the bottom first, you have the acceleration between CPU and GPU on V100, so the next to last NVIDIA generation. And since this system had 40 cores per node, what we do is that we compare 10 cores to one GPU, 20 cores to two GPUs, and 40 cores to four GPUs. So basically trying to have the same costs between the CPU and the GPU and see what the acceleration is. And basically you can see we have accelerations up to factors 5 from CPU to GPU. And this acceleration translates to between generation that you have on top. You have the V100 and the A100, the V100 in blue, the A100 in green. And this was done on the dual system up to 1024 GPUs. With very good scalability again. And lately, we've been experimenting on new systems like the Genoa processor, 192 cores per node, and the AMD GPU systems like the ones that in Lumigi. And here you can see the computational efficiency between CPUs in blue and green and the GPUs in gray. So basically, the GPUs are much more faster here. This is just experimental in the sense that the GPUs for the GPU acceleration for AMD still an ongoing work. But this has allowed us to do this kind of simulations, and this was a simulation that was done last year on Iran again, which is a full combustion chamber simulation with the turbofan, with the turbine, and the combustion chamber. All moving parts are resolved, and everything is done on a single instance. So this is full code coupling live done on this system. And this is what was one, is actually the first simulation of this kind in the world. Now, of course, this has allowed us to work on other applications. Since we worked on the turbines, it can be used for wind turbines, and we are looking at renewable energy. So this is the idea is to look at what happens between two wind turbines when they follow one to the other, to see what happens to the contrails and see the power efficiency. And this is an ongoing work that we've been doing on the Adastra system in the south of France, trying to do an 80 wind farm demonstrator. Here you can see some basic results we've been doing on this AMD GPU system, and it already has yielded interesting results, especially this 30% 30 times gain compared to a CPU simulation. And now we have a much more resolved simulation that is ongoing, where you can really see the turbulence generated by the wind farm. And with very good power distribution compared to the experiments, we actually match now mostly what happens between the rows and the wind turbines. Now, in EXCELLERAT, one of the focuses has been a mesh adaptation. As I mentioned earlier in the code, it was added during EXCELLERAT. And the idea is to have physics-informed static mesh generation. So looking at the physics and creating a mesh that is fully aware of what the physics should be. And you can see on the left the application to a nozzle. And I dare you to try to do by hand the type of mesh that you can get with this static mesh generation, where it is perfectly matching the structures with the shocks. And the other application that we were working on phase one and we are going to start in phase two again is safety applications. So explosions, and for that you need to have phone tracking. And this is the application on the right, where you see the propagation of the combustion kernel, the mesh that is evolving, the turbulence that is generated on the top. And as you can see, it works quite well and gives really interesting results, at least it can be seen. And this will be published soon. And lastly, one of the things that we've been trying to do is a collaboration with the RACE COE. The idea is to use AI to replace models, because as most of you know, when we develop models, we have hypotheses on the application. But when you look at the combustion chamber with the turbine, it's almost impossible to get all the hypotheses right. So the idea is to use AI to circumvent this drawback and have models that match the data and not necessarily have hypotheses behind them. So the idea is to couple the AVBP code with deep learning, neural networks or graph neural networks. The code working on the CPU and the neural network working on the GPU. And this is called Fidel. This is a prototype of coupler that uses 3P or MPI to be able to do this coupling. And one of the main applications we've been doing is this subgrid scale combustion model AI, where since when we try to solve this flame it's very wrinkled. It's supposed to be very wrinkled, but the mesh is not enough. Is not resolved enough to do it in the right setup in LES. So we need to account for this wrinkling in the flame. Today we use this charlet model that is able to adapt corresponding to the LES, but this only matches in some cases, and you have the publication here. You have more information on that. So what we do is that we replace this charlet model with a convolutional neural network that adds this subscript flame wrinkling directly to the simulation. and this is done live, and you can see here some of the results. So this is the same explosion application used during EXCELLERAT in phase 1, and this is in phase 2. This is the AVBP simulation. This is the neural network partition. You can see they don't match at all, and for the domains, of course. This is the classical simulation, and this is the one with the coupling. And here you have the overpressure simulation. And you can see the propagation of the kernel. Don't mind that it's time shifted because this experiment is very, very sensitive, even in the real world. What is important is that we get exactly the same behavior of the behavior of of both simulations compared to the experiment within the error bar. So we are now able to couple this model, and all other models can be replaced, like for example, the law of the wall and other stuff. And some people are working on the CFD team on replacing the full numerical scheme with this. So this is a quick overview of the code and the application we've been doing, and what EXCELLERAT has been allowed us to do. And if you have any questions, I'm here to answer.
So thanks a lot, Gabriel, for this wonderful presentation. And before we go to the questions, I can plug in that actually, as you mentioned, Race and your collaboration with Race, that Race will be present their application in the next code of the month. So people can just stay tuned to that. Yeah, and then the floor is open for questions.
Morris here. I had raised my hand.
Yeah. Please, Morris.
Yeah, sorry, I'm just out of the car. My question would be, we have vertical wind wheels in Iceland, right? And they do 3D printing with wind tunnels and so on, and no CFD yet. How much effort would it be for this code, let's say, to rearrange from a standard ventilator to a vertical ventilator?
Well, it's more, it's just depending on the 3D model, to be honest. So I don't think it's a very big problem. It's just a question of setting up the 3D model.
So basically a new mesh and so on of the wind wheel itself and so on.
Yes, the numerics and the whole code don't have any hypothesis on the orientation of the fans or whatever. So it should be completely blind to him.
Yeah, quite interesting. Thank you.
Yeah. Yeah. I saw someone on the chat asking how do you access the code. So currently, the best solution is to contact me directly, and I will send the message to the person involved on this. We will add something on the EXCELLERAT portal so that people can ask directly as well there. At the moment, we haven't added this feature on the portal.
Yeah, if I can jump in this at this question. So if someone wants not only to access the code, but also needs an HPC system, would it be possible in the future to maybe use JU systems for that? Will it be?
Yes.
Yeah.
Yes, the code today supports Lumi because it's the main one that we have access to, but we should have access to Leonardo soon, and the idea is to support any of the GU systems. Yes.
Thanks. Are there further questions?
If I may ask one question, what is the original coordinate system for the code? Is it Cartesian or?
By default, it's Cartesian, yes.
But you say by default, right? Right. But is it possible to rearrange the coordinate system in the code, or is it something that could be customized somehow?
There are some options to do for rotating flows and for rotating setups and so on to do a relative coordinate system. Is not overly complicated to change because the coordinates, in fact, are not involved in too much things. We use them as a reference, but most of the indexes are on the nodes. So it's if you need another different coordinate system, it's not super complicated to be used. No.
Okay, thank you.
So I'm looking. Are there further questions? Okay, this does not seem to be the case. So I would remind everybody here to fill in the very brief questionnaire we have prepared for you. And otherwise, I would ask you to stay tuned because we will have the next Code of the Month session in about 1 month about race AI codes. So if there are no further questions, indeed, we would already be done for today. And thanks a lot again to Gabriel for this wonderful presentation.
I think someone asked if the presentation will be made available. I have sent the presentation already, yes.
Yeah, so we can make that available and we will have also the recording from today.
Thank you.
Okay, thank you.